Hello class, today we're going to continue with 4.1 basic concepts of probability, and today we're going to discuss the concepts of a Venn diagram and the concept of complementary events. So what is a Venn diagram? Let's read. A Venn diagram is a diagram, obviously, in which we can represent by means of areas their respective probabilities of events in a given sample space. So by now, you already know what the sample space of an experiment is, right? And you also know what an event is. So let me give you some examples of what I mean by this. For example, in here we have a Venn diagram for the sample space of throwing a fair die. So let's suppose we throw a fair die, and we want to represent visually the sample space of this experiment, right? And as we know, the sample space is usually represented by a U, and the sample space is a set of all the possible outcomes. For throwing a fair die, the outcomes are, as we know, the following. This is just a fair standard die, nothing weird. And we know that these are all the possible outcomes. And since it's a fair die, we're making the assumption that it's a fair die. Each of these outcomes have an equality of probability, right? The probabilities of the die coming up at 1 or 2 or 3, etc. are all equal by assumption. How can I represent this visually? We can basically draw an area, a large area. In this case, it's a rectangle. And then we can divide this area, the whole area, into sub-areas, so to speak, like this. You see? This big area has 6 separate areas, all of which account for one of the possible outcomes. And if I'm saying that this die is fair, then the way in which I should draw these Venn diagrams is that all the areas representing each of the possible outcomes should be of equal size. So this area should be the same as this area, as this, as this, as this, and as this. You see, that's how it works. It's just a way to represent visually with areas all the probabilities of the outcomes in a given sample space. Now, usually you will encounter Venn diagrams either in rectangular form or in circular form, like this. This is another possibility for a Venn diagram for the same experiment. Instead of a rectangle, I'm drawing a big circle, and I'm basically doing these divisions like if it was a pizza, and I'm saying, see, by representing each of the slices as equal to each other, like they have the same area, I am saying visually, I'm saying that each outcome has the same probability. What about this? You may look at this and you may think it's very weird. It's just as good. It's just as good. This is a diagram, a visual diagram, in which I'm representing all the sample space. Okay, and here I did my best to represent each of these separate areas, this, and this, as more or less equal. So by assumption, I'm telling you that this area is the same as this area, the same as this, the same as this, the same as this, and the same as this. Even though it doesn't look like that, that's understood, right? And if that's the case, then I'm saying by through a visual representation, like if you could measure the areas of all of this, and if the result comes out that all the areas are the same, then that means that all the possible outcomes for this experiment have the same probability. Now let me give you given this experiment, the throwing of a fair dice, let me give you a counterexample of an incorrect Venn diagram. For example, if somebody did this is the sample space represented by U, like, okay? In here I have all my possible outcomes, and if somebody draws this, something blatantly incorrect, for example, let's even exaggerate even more, like this. If you saw this drawn, this Venn diagram. For this experiment, this would be quite incorrect because here I'm representing visually that the outcome 1 is much more likely than the outcome 2, 3, 4, 5, and 6. So this is not a good idea for a Venn diagram given this experiment. Okay, so you can draw the Venn diagram in any way you want, any shape. It doesn't have to be a rectangle or a circle, even though those are the most popular. It can be anything, any closed shape. And inside, you're gonna represent by regions as if they were countries, more or less. So you have in here one country, and in here another country, and here another country, and these countries of your continent represent your individual outcomes. Yeah, I think that's a good analogy. Try to think of the sample space as a continent, and try to think of the individual outcomes. Try to think of the countries as the individual outcomes for any given experiment. What are we having here now? We have the following: a Venn diagram for the sample space of throwing a die, in which one has twice the probability than the other results. Now in here, even though it doesn't look like so, I did my best to try to convey visually that this area is twice this, or this. I know it doesn't look like so. I could have done it better. Let me try to do it a little better. What about now? I think that's better. Okay, so visually I'm saying that the outcome 1 has twice the probability than any of the other outcomes. You see? So basically, a Venn diagram is a visual aid, or a diagram. That's what a diagram is, right? A visual aid, in order to represent by means of areas the probabilities of individual outcomes or events. Let me make a pause and let me come back with you in a moment. Okay, some more examples. Now that we talked about the Venn diagram in relation to the individual singular outcomes, let's talk about the Venn diagram in relation to events. For example, let's consider the same experiment. We're still only experimenting with die, okay? With dice. I'm sorry, that's plural. So, for example, suppose I throw a fair die, and I'm interested in the following events: event A and event B. The event A, I want to define it as the die comes up even. So what outcomes, that's actually set notation, what outcomes compose event A? The outcomes 2, 4, and 6. And event B, the die comes up odd. What singular elementary outcomes compose this event? Well, 1, 3, and 5. Therefore, since as many outcomes comprise the event A as outcomes comprise the event B, then the regions or the areas representing the probability of event A and the probability of event B should be the same. This area should be the same as this area. That's how it works. So this would be a Venn diagram for such experiment, in which event A is represented in this way and event B is represented in this way. Now I want you to notice something, guys. The event A, the area for event A can be further partitioned. Partition, right? What I mean is this: since event A is comprised or composed of these singular 3 outcomes, then I can divide this region into something like this. One part, 2 and 3 parts, you see, and each of these parts would represent each of these outcomes. Okay, you see, and the same for event B. All of these are supposed to have the same area, 1, 3, and 5. You see, and the thing I want you to notice is this, guys. The difference between an individual outcome, such as getting 6, or getting 4 or getting 2 or getting 1 or 3 or 5. And an event is that when you look at the area, let's consider this area for 4. When you look at the area representing the probability of this singular outcome, then you realize that this area cannot be further partitioned anymore. You cannot divide this area into something more elementary, and that is the difference between event. I mean that's a way to explain the difference between event and a singular outcome. When you draw the Venn diagram for all the outcomes, for example, if you drew for any experiment, you drew the Venn diagram for each of the outcomes, like this is an outcome, this is another outcome, another outcome, another outcome, and another outcome. Then these areas cannot be further broken down. You see? But when you consider a Venn diagram in which you have events, for example, event A, event B, and event C, then these events are composed of singular outcomes, and therefore you can partition each of these areas into those elementary singular outcomes that comprise the event A. That's a way to understand the difference between event and outcome. Even though an outcome can be, in most cases can be also understood as an event, not all events are outcomes. That is the difference. Every outcome can be considered as an event, but not all events can be considered as outcomes. If you have difficulty understanding this which I'm saying, please let me know in a moment. And here I have another example. Okay, look at this. We have the same experiment again, and we have two events. The die comes 1 or 2, that's event A, and event B, the die comes up 3, 4, 5, and 6. So clearly, the area representing the event A should be less than the area representing the event B. And event A can be further broken down into the outcome 1 and the outcome 2, and the event B can be broken down into the singular outcomes 3, 4, 5, and 6. So I may do something like this. I guess 3, 4, 5, and 6. And I'm assuming that all of this area, this area, this area, this area, this area, this area are all the same. I don't have any way to actually make sure of that, but you get the idea, right? Now, more complicated examples. Consider this experiment, guys. Let's choose an integer from 1 to 10 at random. How? We don't care. At random. And here I have a Venn diagram in which I'm representing the probabilities of these three events. Event A, the integer that we chose is less than 6. Event A. And event A is being represented by this white shadowing, all of these. Okay, so in here I have all the individual outcomes 1, 2, 3, 4, 5, and 6. They all live in here. Okay, now event B. The event B, I'm defining it as the integer that we chose is greater than, I'm sorry, I wanted to, let me remind what I said. The integer is less, well, let me change the names because I wanted to do it the other way around. It's greater than, let's call this A and B. Okay, forget about what I said, guys, and let's consider these ones better because I want to have some order. So the event A, the integer, no, it's actually correct. I'm sorry, guys. This is what happens when I do this in a single take. Okay, the event A is the integer that we choose is less than 6. Okay, so yeah, that's right. It goes from 1 to 6 and is represented by this white shadowing. Perfect. Now, event B, the integer that we choose is greater than 4. Greater than 4. So what outcomes do we have in here? We have all of this yellow shadowing in which we have only integers from 5 to 10. Okay, 5, 6, 7, 8, 9, 10. Okay, so I repeat. What outcomes comprise event A? 1, 2, 3, 4, and 5. Alright? I cannot put the 6 because 6 is not less than 6. Okay, putting the 6 right here would be a mistake. Now, B, the integers greater than 4. What integers from 1 to 10 are greater than 4? 5, 6, 7, 8, 9, and 10. All of these. Okay, and it's represented by this yellow shadowing. And we can see the following. We can see that these two events, event A and event B, overlap. They overlap right here, guys. Right here, can you see? Event A and event B overlap a little bit in this region. This region in here, this small rectangle, is both part of A and is both part and is also part of B. What is this event though? It's the event in which the integer that we choose is 5. 5. This single rectangle accounts for the probability of getting 5. Why? Because 5, I mean, how can we understand the overlapping? Well, because 5 is both in event A and is also in event B. That's why the overlapping. You see, so events can overlap. Events can overlap, but individual outcomes cannot. That's another way in which we can establish the difference between an event, a proper event, and an outcome is that individual outcomes cannot overlap in this way. Let's perform another experiment. Let's suppose we choose a person in the street and we observe her or his characteristics, his physical characteristics. And let's just assume that we only care about the type of hair that this person has. And let's assume by hypothesis that it can only be either blonde or black. No other possibilities for hair. And the other only characteristic that we will observe is the color of the eyes, and let's assume that it can only be either brown or blue. So we only care about these two characteristics: color of hair, color of eyes, and we only have these two options for each. We will ignore any other characteristic about people. How can I draw more or less, this is just an intuition or a hypothetical Venn diagram. I'm obviously not researching anything. It's just what I think should be given the Mexican population, what we are used to. Well, let's consider first the color of hair, blonde or black. So we know that many more people have black hair than blonde hair in Mexico. And if I want to represent that in this Venn diagram, I would have to draw something like this. More or less, I guess. Okay. This is event B, in which the person has black hair. And this is, well, instead of blonde, since I don't want to confuse the letters, well, I didn't see that coming. Yeah, let's call it yellow. Yellow hair. And this is Y for yellow hair. Yellow hair. And what this represents is that there is much more probability of this person having black hair than yellow hair. Now, how can I represent in the same diagram, in the same Venn diagram, the color of the eyes, either brown or blue? I'm going to write BR for brown and BL for blue. So once again, the great majority of people that we see have brown eyes. So I could do something like this. That in which all of this represents brown, all of this area, and all of this area represents blue eyes, all of this. So instead of writing B here, let me put it outside. I think that's much better. I want to have order. This is brown eyes. This stands for black hair. This stands for yellow hair. So you see, we have all of these events. All of this area, all of this represents having black hair. All of this area represents the probability of this person having yellow hair. All of this area represents the person having blue eyes. And all of this area represents the probability of this person having brown eyes. Now, what could each of these sections mean? Well, this larger area, this is the greater area, tells us of the probability of encountering this person having black hair and also brown eyes. So this is black hair and brown eyes. This is black hair and blue eyes. This is yellow hair and blue eyes. And this is yellow hair and brown eyes. So you see how this works. Different events can overlap. Now let's deal with the concept of complementary events. Complementary events. What is this? Let's read. In any random trial and for any given event A on such trial, we define the complement of A, represented by this symbol. It's going to be an A and a little apostrophe right here. Okay, this is read as not A, or also the complement of A. I repeat, this symbol is read as not A, like this, or the complement of A. Some people also call it A prime. A prime. This symbol is called prime in mathematics. So either way, it doesn't matter. What is it? It's the event in which A does not happen. And it's a very simple idea to understand. I'm going to give you 3 examples. Example number 1. What is the experiment? Throwing a fair die. Perfect. Let's define the event A. The event A, I'm going to define it as the die comes up at 2. Then, once I have defined this event A, then not A, or the complement of A, is the event in which this doesn't happen. It's the negation of this. And basically what that is this. The die does not come up at 2. That's the event A. A prime, I'm sorry. A prime. Okay, what are the possible outcomes for this experiment? We know that it's 1, 2, 3, 4, 5, and 6. All of them are equally likely. And therefore, event A, which is the die comes up at 2, has just one possibility out of 6. So the probability of the event A is 1 over 6. Very simple to calculate. Now, what is the probability of the event not A? Or what is the probability of the complement of A, which is that the die does not come up at 2? Well, we have 5 possibilities, right? We have 1, 3, 4, 5, and 6. We have 5 possibilities out of 6 ones. Out of 6, I'm sorry. And therefore, we say that the probability of the complement of A is 5 over 6. Second experiment. Let's throw 2 fair coins. And so let's define the event A as we get at least 1 heads. And therefore, once I have defined this event A, I can define its complement, which is we don't get any heads. If the event A is we get at least 1 heads, then the negation of this event would be that we don't get any heads at all. Now, what is the sample space for this particular experiment? As we know, because we have already done it, the sample space is that the coins land heads heads, or heads tails, or tails heads, or tails tails. So my sample space for this experiment is composed of 4 individual outcomes, which are represented by ordered pairs, like this. Okay, so what is the probability of the event A? We get at least 1 heads. At least 1 H, basically. Well, how many cases favorable to this event do we have? This is favorable to the event A. This is also favorable because at least we have 1 heads. And also this one. So there are 3 cases favorable to the event A out of 4 possible cases. So the probability of the event A is 3/4 because there are 3 cases favorable to the event, which is this, this, and this, out of 4 possible outcomes. So it's 3/4. Now, what is the probability of the complement of A? What is the probability of not A? Which is we don't get any heads. Well, the only case favorable to such event is this one, right? This is the only case in which we don't get any heads, which is just 1 out of 4. There you go. So this is the probability of A. This is the probability of the complement of A. Perfect. One last example. Let's choose a random item at OXXO. And let's define the event A as the item is some food. Perfect. Now, what would be the event not A? Well, basically, the item that we choose is not food. If the event A is that the item is food, the event not A, or the complement of A, would be that the item is not food. What could it be? I don't know, a magazine, I don't know, soap, I don't know, we don't care. So let's see. Now, in this case, the probability would be very hard to get, right? To calculate what is the probability of A. We don't have enough information to say this. But let's assume as a hypothesis that the probability of choosing food is, let's say, 1/3. No, let's say it's 2/3. There's a lot of food in OXXO. So the probability of picking food is 2/3. Then I guess it's clear to say that the probability of its complement would be 1/3, right? Because it's all the other possibilities, right? And this leads us to one of the basic axioms of probability, which is that the probability of an event A plus the probability of its complement, the probability of its negation, should be equal to 1. If you want to visualize that in a Venn diagram, then we have the sample space for a given experiment. If we represent the event A by this area, then all that is outside this area, all of this area, is not A, is the event not A. And as we can see, the event A and the event not A, which is all the cases in which A doesn't happen, they form or they fill the totality of the sample space. You see? And since the probability, let me write something down that I haven't told you, although it's quite intuitive. The probability of having something in the sample space, any outcome, has to be 1, right? We actually say that the probability of the sample space is 1. What this means is that the probability of an outcome in the sample space occurring has to be 1, because once I have defined the sample space, then at least one outcome has to come up, right? So at least something has to appear. So basically that's what we mean by the probability of the sample space being equal to 1. And therefore we can see that this region, this area, and the region outside it form the totality of the sample space, and therefore the sum of the probabilities has to be equal to 1, which is also very simple to understand because we have the security. We have the security, or we can make the affirmation that in any given experiment, guys, either an event happens or it doesn't happen. You see, either this happens, either this is true or this is true, and that's it. We don't have anything in between. For example, in the first die, the die comes up at 2 or it doesn't, and both probabilities have to be, therefore both probabilities, the sum of them, have to be equal to 1. So this is one of the basic axioms of probability, and we're gonna use it in order to solve some problems.